So, to study this non-linearity, we are going to do a simple numerical experiment. Okay, very simple numerical experiment. What is that experiment? This is my domain D. My domain D has only two objects. Okay, two objects x1 and x2. And further, what am I assuming to make my life easier? That I know the boundaries of these objects. Okay, I am going to make my life really simple. I want to restrict myself to two variables because, why would you do that? Because I can visualize 2D, I cannot visualize 10D, right? So, I want to restrict myself to 2D so that I can visualize it. Okay. So, now what should I do? This is my 2D, this is my two variable problem. So, my contrast x is simply x1, x2. Okay. And what I can do is I can plot this for different values of x, just to see, is there one parabola, are there several parabolas, what is there, right? And it's in 2D, so I will not have a line, but I'll have a surface. Okay. Not just that, I can also look at the direction of the gradients, right? What will the gradient direction tell me? It will tell me maximum change, and it will tell me that if I did, for example, a gradient descent algorithm, which direction will the search go, right? So, there are two simple gradients that I can think of from the previous page. One is I can take a gradient of this guy, where I assume u is constant. So, it is a simple gradient. So, this is what I call the linear gradient. Or I can be brave and take a gradient of this expression, and that will be called a non-linear gradient. Obviously, non-linear is exact, but it is computationally very tedious. So, that is what I am going to study in the next numerical experiment. Okay. All right. Yeah, okay. So, I am saying assuming u is constant, that means my gradient, I am taking the gradient of s minus gs ux. That means u is constant. So, when I take the gradient, only the x dependent terms are this guy. Okay. And non-linear means over here, u is a function of x.
So, this system is like
two homogeneous objects in some medium. Okay, and their permittivity is x1, x2. No, okay. So, what I am saying is that this entire object has permittivity x1, not one pixel, but this entire blue object is x1. And this entire square object is x2. Those are the two variables. So, you are saying that contrast vector should have been actually the size of the number of pixels of this, right? This whole. So, actually, so this actual x would have been a very long vector with x1, then 0, then x2, right? That is how this contrast vector would have been. But if I know, to make my life easier, I am going to give you this additional info that this entire object is just one x1, this entire object is just one x2. So, I can write this in terms of some matrix which is composed of ones and zeros multiplied by x1, x2, right. If this is size n cross 1 and this is size 2 cross 1, I can get this to be a n cross 2 matrix, which will just have ones and zeros in the right places, so that I get this. So, that I work with just two variables, right. So, this M matrix will then get multiplied over here. So, these kinds of tricks we do to make the problems more visualizable. Otherwise, you will just throw up your hands and say n variables I can't visualize. So, you will not get any intuition.
Then it should be 3 variables, right?
What is the third variable?
VD,
0. Remember, x is equal to epsilon r minus 1. So, if this is vacuum, it's x is equal to 0, which is given to me. I am not going to try to find it. The question is, if you want to study this in its full generality, then you will have to make this to be blood, you will have to do everything of that. So, you will make a very complicated problem and get no intuition from it. So, we are solving a simpler problem where we know everything except these two. This itself is going to be difficult. So, let us visualize this, right. So, that is why I am saying only two variables.
So, initially we know the value of x1 and x2.
We don't know the value of x1, x2. We don't know the value of x1. So, I am going to try to solve this problem to find out what is that x1, x2 which gives the best agreement with S. the scattered fields. That is the experiment. Okay. So a lot of a priori information has been given to you: the location of the objects, the fact that they are homogeneous, and the fact that there is nothing else. That's a perfect example of a priori information.
So what do you mean by assuming u constant?
Assuming u constant means that when I look at this objective function and I take its gradient, I assume u to be constant and not a function of x. So then s minus ax ux, this is a linear functional. So to take gradient is very simple. That's what I mean by assuming u constant.
But you know it is not.
It is not constant. So what I do is that I assume u to be constant at that iteration, find out the nu x, right. So I assume u to be, I calculate u from x, assume it to be constant and put it in over here, find out the gradient, which gives me a new value of x. That x I plug in and get a new u, put it back in, keep it constant. So it's like a poor man's way of doing this thing. Ideally what you should do, you know that u is a function of x, so put the whole thing over here, and that is what I am calling a non-linear approach. Okay, so these are the two different cases. So now let's see what happens. So we have set up the problem very well. Now let's look at what happens. So what I am plotting is the value of this objective function s minus gsux. Okay, what are my axes? x1, x2. So let's first look at the left hand side. Okay, this is a low contrast problem where the true solution is x1, x2 is equal to 0.5, 0.5. Okay, so dark blue color corresponds to lowest value and yellow color corresponds to highest value of cost function. Okay, so what I am showing are these contour plots, right. So it's like a topography map of a hill, right. So yellow value is the peak, blue values are the valleys. And what are these arrows showing you? These arrows are showing you the direction of the negative gradient, okay, because I want to always go in the direction of negative gradient, that is the steepest descent, that will take me to the minima. So you notice over here, if I start from the origin, which was our guess for Born approximation, I fall into approximately the correct answer, half, right. If I had started from, let's say 1, 1, 1, would I still go into the correct valley? Would I still get the correct answer? Yes, because in this region over here, all the gradients are guiding me to the correct valley. So it's like I have one valley over here, right. So even if I had started from here, what will happen? These arrows will nicely guide me back in over here. So there is only one valley. I start anywhere in the neighborhood of that valley, I reach the correct answer. Very good. On the other hand, supposing I said no, I will start my search from, let's say 6, 6. Supposing I start from here. Where do the gradients take me? They take me in some weird direction over here, and then here the gradients become very small in magnitude. The length of the vector is the magnitude of the gradient. So I reach here, and what happens? I cannot proceed any further. The gradient is 0, but what is the value of the cost function? It's not minimum, right? So where you initialize matters, because now this is a non-linear optimization problem. But if I started anywhere close to 0, not being very strict about it, I reach the correct answer. That much is clear. Okay. Now let's take another problem. Okay. So before coming to this, let's just summarize over here. So for a low contrast object, it does not matter where you start from and you arrive at the correct answer. Why? Because the true minima and the global minima are very close to the origin. So if I started from 0, 0 or its neighborhood, I reach the correct answer.
But if you started around 0, 8.
If I start at 0, 8, then I reach the wrong answer, right? That's correct. And many other points. If I start at 8, 1 also, I reach the wrong answer. So there are many regions in this which will take me to the wrong answer. But since the literature started with the theory of Born approximation, they always started with 0, 0. So they always reached the correct answer. So they got satisfactory answers. And then at some point they realized, oh, realistic tissue need not have very small values of contrast, but our methods are failing. Now you can, because you made a simple 2D problem of it, you can see this and tell why it is failing. It's failing because there are so many hills and valleys in between that you are not able to reach the correct answer. And we can see that in the next problem on the right, where the true answer is x1 x2 is equal to 3 7, right. So, the correct answer is sitting over here. If you started from 0 0, what will happen? Disaster, right? I am going down, I am going to get negative values. So, there is no hope actually. I just don't know where to start from. If I start from some random point, if I start from here, again I go down. If I start from, let's say, here and I reach over here, gradients are 0, right. Okay, so it's a lot of computational work to produce this diagram. I am doing this diagram to aid my understanding. This is the diagram as a 2D plot of values of s minus gs into ux.
For that x1 x2.
For where the true x1 x2 is 3 comma 7 and s is corresponding to that, and now different values of x and u, what does the value of the cost function look like. So, in real life I will never have access to this, because first of all it will be maybe a 10,000 variable problem. So, how do I visualize 10,000 dimensions? Yeah, this is for that, it's for this only.
So for this case you have something else complex.
Yeah, exactly. For this case all I had to do was make x1 x2 from half I made it 3 7 and boom, I am in deep trouble. I have no good way of knowing where to go. Right. That's one huge problem over here. Only if I start somewhere in roughly this domain over here, then will I land up at this problem over here. So that's why I need some a priori information.
Is there any nice theorem that can
Nope. So all your weight of machine learning and deep learning and all of that can be applied to this to try to learn where might be the correct value from a lot of data to tell you where to land up in. Okay, this is why this is a very challenging research problem, and realistic tissues, realistic landmines and all, they will have high contrast, right. So that's why you have to live with this problem. As was one suggestion was suggested over here. So for example, here we made 3 comma 7, right. So this was 3 and this was 7, and this was a challenging problem, right. Now this contrast was defined as epsilon r minus 1, right. Now that is a simplistic definition. The true definition of contrast is actually like this: chi r is equal to epsilon r relative minus epsilon b by epsilon b, where epsilon b is the permittivity of a background medium. So if background medium was vacuum, it is epsilon r minus 1. But if I know that the true permittivity is roughly going to be in this high range, then what I can do is I can fill the medium with some kind of what is called a matching liquid or matching material, whose epsilon b is, let's say, I can take for example something like 5, let's say. So then what will the contrast become? So 3 minus 5 by 5, right, for x1 will become this, and x2 will become 7 minus 5 by 5, right. So these are all numbers which are small, right. Minus 2 by 5 is minus 0.4 and 2 by 5 is plus 0.4. So my problem has become lesser. I have mapped it to sort of this problem. I made the permittivity smaller, okay. But many times this is not going to be possible, because I cannot produce at will a liquid which has permittivity 4 or 5. It's hardly trivial, right. Moreover, in the landmine detection problem, like, forget it. What are you going to pour? Not really. Okay, so the question is, what if we start with m equal to n and then use that? So it may help you in sort of getting into the right quadrant. But the problem is, when I start with m equal to n, I have a m dimensional space and I have got some solution over there. Now when I want to go for a higher resolution, let's say I go to 100 m, now I have a 100 m dimensional space. How do I relate that m dimensional space and this 100 m dimensional space?
the value you have some anyhow the
Yeah, I'll have some value of thing.
change the rate.
So in some sense I have to downsample that solution. I mean, I have, let's say, x1 x2 here. Now you are saying I want to now retrieve this at a higher resolution, 3 cross 3 resolution. Now what do I do? I've got a 2 resolution answer. Now I want to map this 2 as an initial guess for a higher resolution, let's say 3 cross 3. Then what do? I have to,
So understand the
how do I map this to that?
like one grid to the grid.
Yeah, one grid here to one grid there. It can be done, but that's again non-trivial math to do it. And that is done. And that helps us sometimes to get into the right value. But these values can be sensitive. Supposing I started in this value, I reached the correct answer. But if I started, let's say instead of starting here, I start over here, then boom, I go here. So it may or may not work.
But it can be a good approximation.
It is a good approximation. In fact, it is commonly done.